Falling into a black hole is one of the most extreme journeys imaginable, not because a black hole is an empty hole in space, but because it is a region where gravity becomes so intense that space and time themselves change their meaning. From far away, a black hole looks deceptively simple, a dark object surrounded by stars, quietly sitting in the cosmic landscape. But as you approach, the universe begins to behave differently. Gravity grows stronger with every passing moment, and the familiar rules of motion begin to transform. The first dramatic effect you encounter is tidal force, the difference in gravitational pull between two nearby points. Near Earth, tidal forces create the rise and fall of ocean tides. Near a black hole, tidal forces become unimaginably violent. If you were falling feet first toward a small stellar mass black hole, the pull on your feet will be far stronger than the pull on your head, stretching your body into a long, thin shape. This process is sometimes called spaghettification, and near small black holes will destroy any object long before it reached the event horizon. But black holes come in different sizes. Near a supermassive black hole, like the one at the center of the Milky Way, the event horizon is enormous, and the tidal forces at the horizon can be surprisingly gentle. In that case, it is theoretically possible that you could cross the event horizon without feeling an immediate, catastrophic force. This leads to one of the strangest facts about black holes. The event horizon is not a physical wall. It is not a surface you collide with. It is simply a boundary in space-time, a mathematical threshold beyond which escape becomes impossible. Outside the horizon, you can still imagine turning around, firing rockets, or sending signals outward. But once you cross the horizon, the geometry of space-time changes so deeply that all possible future paths lead inward. Even light, traveling at the fastest speed nature allows, cannot return. The horizon marks the point where the future no longer points outward, but only deeper into the black hole. To understand why, it helps to remember Einstein's description of gravity. Gravity is not merely a force pulling objects together. It is the curvature of space-time itself. Massive objects warp the fabric of reality, and black holes represent the deepest curvature possible. Approaching the horizon is not like approaching the edge of a pit. It is like approaching a region where the fabric of space and time is bending so steeply that the direction outward ceases to exist as a route into the future. From the outside universe, black holes appear as dark spheres. But what they truly are is a transformation of space-time into an inescapable geometry. And as you fall closer, another strange phenomenon begins to dominate your experience. Time itself starts to behave differently. Your journey is no longer just through space. It becomes a journey through the most extreme distortions of time that the universe can create. From the perspective of someone watching from far away, something deeply strange happens as you fall toward the event horizon. Because of gravitational time dilation, your motion appears to slow down. The closer you get to the horizon, the more slowly your clock seems to tick compared to the clocks of distant observers. The light you emit becomes increasingly redshifted, stretched to longer wavelengths, fading into darkness. To the outside universe, you never quite cross the horizon. You appear frozen at the edge, gradually disappearing as your signal weakens beyond detection. This creates the illusion that nothing ever truly falls in. But for you, the experience is completely different. Your own time flows normally. You do not feel yourself slowing down. You cross the event horizon in a finite moment. And once you do, The nature of reality changes in ways that are almost impossible to visualize. Inside the horizon, the roles of space and time begin to exchange. In ordinary life, you can choose to move through space in different directions, but you cannot choose to move backward in time. Time is an unavoidable flow into the future. Inside a black hole, moving toward the center becomes just as unavoidable. The singularity is not merely a place in space. It becomes a point in your future. No matter what you do, every possible path leads inward. The direction toward the singularity is as inevitable as tomorrow. This is one of the most unsettling consequences of general relativity. Within the horizon, the singularity is not something you can avoid any more than you can avoid the passage of time. As you continue falling, tidal forces grow stronger. Even in a supermassive black hole, where the horizon crossing might be gentle, deeper inside the gravitational gradient becomes extreme. Space is stretched, time is warped, and the universe outside becomes increasingly unreachable. If you could look outward after crossing the horizon, you might still see the outside universe for a brief period, but its light would be distorted, compressed into strange patterns by the curvature of space-time. The external cosmos would appear to accelerate into the future, while your own remaining time would be limited. The deeper you fall, the less meaningful ordinary concepts become. Distance, direction, and even causality begin to break down. According to classical general relativity, your journey ends at the singularity, a point where density becomes infinite and space-time curvature becomes unbounded. But most physicists do not believe nature truly allows infinities. The singularity is widely interpreted as a sign that our theory is incomplete. General relativity works extraordinarily well in describing gravity on large scales, but it does not include quantum mechanics, the physics of the very small. Inside a black hole, where matter is compressed to extreme densities, quantum effects must become important. Somewhere before the singularity, our current understanding fails, and a deeper theory must take over. The true interior of a black hole may not be a point of infinite density, but something far stranger, a quantum region where space-time itself becomes uncertain. What actually happens inside a black hole remains one of the deepest mysteries in physics, because no information can escape once it crosses a horizon. The interior is hidden from the rest of the universe forever. This makes black holes not only astrophysical objects, but boundaries of knowledge. We can describe what happens outside with great precision, and we can predict what must happen according to our equations, but we cannot directly observe the interior. This has led to some of the most profound questions in modern science. One of these is the black hole information paradox. In quantum physics, information cannot be destroyed. The exact state of particles should always be preserved in principle. Yet, black holes seem to erase information completely. Anything that falls and appears lost forever, hidden behind the horizon. Stephen Hawking added another twist by showing that black holes are not entirely black. Quantum effects near the horizon cause black holes to emit faint radiation, now called Hawking radiation. Over unimaginable timescales, a black hole can lose mass and eventually evaporate. But if a black hole evaporates completely, what happens to the information of everything that fell into it? Does it vanish, violating quantum mechanics? Or is it somehow encoded in the radiation that escapes? This paradox suggests that black holes are keys to a deeper theory of reality, one that unites gravity and quantum mechanics. Some ideas propose that information is stored on the event horizon itself, like a hologram, and that the surface of a black hole contains the data of everything that has entered. Others speculate about wormholes, hypothetical tunnels through space-time that might connect distant regions of the universe. But there is no evidence that wormholes are traversable, and the interior of black holes remains inaccessible. What is certain is that black holes represent the most extreme environments in nature. They bend space-time to its limit. They slow time, trap light, and challenge our understanding of physics. They are not merely cosmic destroyers, but cosmic questions made real. To ask what happens inside a black hole is to stand at the edge of human knowledge, looking into a region where the familiar laws of the universe may transform into something entirely new. Black holes remind us that the cosmos still holds mysteries beyond imagination, and that even in the darkest places in space, the universe continues to reveal clues about its deepest structure.